Yesterday, I showed you how to determine half-life given problems like this, and I assigned this problem to you, which follows that same pattern. Okay, we did two examples. This was the second. We actually did an example before that just to kind of set it up. That was a little bit more simplified than these. So the question is, vanadium-49, when you write a name like that, 49 is the mass. Okay, it's not the atomic number, it's the mass. Vanadium-49 has a half-life of 330 days. If you start with 400 grams, how many half-lives will have passed if only 12.5 grams is left? So what we're going to do is we're going to keep going through that half-life system until we get to 12.5 grams and see how many half-lives that is. Okay, so we're starting at time 0. That's what that T sub 0 means. We're starting with 400 grams. And at the beginning of our time periods, we have 0 time. That's what we call our beginning point, okay? So we're going to create a kind of grid here to kind of keep up with everything. All right? And so at the first half-life, which we symbolize as T sub 1, time 1 for the first half-life, half of this material will have gone. That's what half-life is. Half of it will decay. So we'll have 200.0 grams. And that's our first half-life, which is 330 days. I'm going to use D for days here, okay? All right. The second half-life, which we're going to symbolize as T sub 2, half of this is going to go. Not the half of the original, not the whole thing, but half of this is what's going to be disappearing. So that's 100.0 grams. And that would be another 330 days, which is 660 days. All right, then for the third half-life, T3, and that's 660 plus 330 days. So another 330 days will have passed. That's 990 days. Half of this goes away, and that's 50.0 grams. Then T sub 4. Half of this goes away. That's 25.0 grams, and that's another 330 days.
Do we have to put grams?
You need to have grams written somewhere because those numbers don't have any meaning unless you tell me what they apply to. Yeah, I said you could go whenever Dominique got back. Okay. Let's see. Oh, that's not what I wanted to do here. So let's see, 990 plus 330, and that's 1320 days. Okay. And then T5 for the fifth half-life, we'll have 12.5 grams left. And that's at 1320 plus another 330 days. So that's, oh, that's not right. I think I just multiplied. 1320 plus 330, and that's 1650 days. Okay? So the question is, how many half-lives will it pass? That's 5 half-lives. The amount of time, the actual days, is 1650. The question asked, though, what the question is asking for is how many half-lives. That's the number right there. Okay? All right, let's go through the band of stability then. You have to have a title.
Yes, sir.
Band of stability. Okay? All graphs must have titles. All right? You have to have axes labels. And for the band of stability, we mark this as 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. You could put 100, but we don't go past 82 anyway, so I could stop right there. Then you need to label what these numbers are about, and those numbers are about the number of protons. Okay, that's what it's about. Number of protons. Then we have to label the vertical axis as well. And that's the number of neutrons, you're right.
Y'all go by tens?
Yeah, go up by 10 on this one. I've set it up so you can go up by 10. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140. Okay? And this is the number of neutrons. So I'm going to label this as the number of neutrons. Okay? Now then, all graphs must have, and this goes back to Unit 1, we taught you how to do formal graphs. All graphs have to have figure labels. And since this is the first one on this document, we're going to call this Figure 1. And you don't have to describe it in exactly the same words that I describe it. You have to describe, in general, what needs to be said. And that is, there are three things that you always put in a figure label. What's in the graph, why it's important, and what is the pattern you see. Okay? Now, this is not the kind of graph where we make predictions about things, so we don't really need to have that last thing on this one. Okay? It wouldn't hurt you to have it. But what's in here and why it's important are essential for this figure label. So what is in here is we're comparing protons against the number of neutrons to see what are the stable isotopes for all the elements that we have stable isotopes, or for which we have stable isotopes. Okay? So you always have to write figure labels anytime you have a graph. Okay? So we could say it this way. This is a plot. I mean, technically it's not a graph because we're not, don't have bars, don't have circles, don't have the best fit lines, anything like that. This is a plot comparing. If you said graph, I wouldn't count it wrong, but it's technically a plot comparing the number of protons to the number of neutrons for all the stable isotopes. So we said you have to have what's in the graph and why it's important. What's in the graph is protons compared against neutrons, and why it's important is for the stable isotopes. Oh, sorry, stable isotopes. What?
We have to put this on.
You always have to have figure labels for every graph. Every graph has to have figure labels.
I've never seen it before.
So you took part off of that?
I did. Okay?
Why did you take part off of that? So you didn't have to.
Now then, the boundary lines for these this band of stability were two angled straight lines here, and the two lines were, the first one was a 1-to-1 ratio. So for every 1 you go over, you go up 1, or if you go over 10, you go up 10. So that's a 1-to-1 ratio. Okay, over 1 up 1, over 10 up 10, over 20 up 20. Okay. So just going to do this right here, and that's where you have over 40 up 40, over 50 up 50, and so forth. So you're going to have a straight line that goes like that. Okay? And then the other boundary line above that is going to be over 20 up 30. Basically, it's over 1 up 1.5, because every time what we're looking for is 1.5 times, or the protons are going to equal 1.5 times that number of neutrons. So the way that I taught you to do that, the way we talked about it in class to figure that out, since going over 10 and up 15, that's a little hard to figure out. It's a little bit easier if we just go straight to 20 and up 30. And then another 20 over and up 30. Another 20 over and up 30. Another 20 over and up 30. Okay? That makes sense?
No. Do it again.
Over 20, up 30. Over 20. Oh, I missed one. This is 30 here. Over 20, up 30. Over 20, up 30. Over 20, up 30. So I've actually put those marks in the wrong place. Okay? Got that? Over 20, up 30. Over 20, up 30. Over 20, up 30. Okay? And so that's our upper boundary line, at least upper going this way.
What's lower?
Huh?
The 1-to-1 ratio is the lower one. Okay?
What we doing on that one?
Over 20, up 30.
Oh, 20 up 30.
And what's the second one called?
Over 20, up 30. Over 20, up 30. Over 20, up 30.
Over 2.
You hear me? But Mr. Taylor,
I heard you, but I'm ignoring
you
you.
answer my question. But you taught us just like on Wednesday, bro. You giving us the test like 3 days later. I'm there for this.
I need you to be quiet and pay attention. Yep. That's it.
You can ask me last question.
Can I get up 30?
No, over 20, up 30. Over 20, up 30. Over 20, up 30.
So that's right there.
That one's right.
If I mess
Yeah.
up, it
All right. Now, there are no stable isotopes beyond proton number 82. So here's 90, here's 80, there's 5 markings in between. So this is 82 right there, and that's the last element. 82, element 82 is the last element for which there is a stable isotope. All right. Since there are no stable isotopes beyond element number 82, then we want a vertical line right there to show, just to help us figure out we don't want to go past that. Okay? So we're just going to have a line at 82 because we don't want to go past that because that's our last stable isotope. Okay. No, that's 82. That's 82.
It's not 80. Look at it.
I realize that, but there's only 5 markings in between 80 and 90. That makes every one of those markings 2.
So you said
2. 82.
And you just draw a line all the way down?
Well, basically you don't need to go past it up here. It's the main part. You could draw it all the way down. That's what I did the other day. Okay? Basically, we don't want to go past 82. All right? Hey,
So we're starting at 82 and going where? Down.
all the way to the top.
I mean, I get the bottom
To the
line.
top to the right. What number exactly?
That's 82. Protons equals 82. If you say a number on the x-axis equals 82, that's a vertical straight line. Okay, yep.
I don't understand the top line.
This line right here?
Yeah, I get the first line, but I don't get the.
It's like up to. Wait, you go over to.
Over to
Up 30.
Yeah. I mean, I could give you we could go with a,
A 1 over 1.
well, a line, an equation for a line.
No, we good. No, ain't that
Oh, no.
I think it's easier just to remember over 2 up 3 than trying to remember the equation for a line. But that's, Okay. And then we need a vertical line at 15. Now, guys, since this is every one of these little small markings is 2. If this is 10, that's 12, 14, 16, 18. So right here is 15, okay? I need a marking right here at 15. Okay? A marking right there at 15.
You have to do those at 15?
That would be a really good idea because of the way that this plot behaves. It would help you a lot if you do that.
I
Huh?
have a question.
No, I won't count on points for it if your plot is correct.
I don't know. I have a question.
Yep.
Instead of getting the number from.
Hold on, how is that 15?
Never mind. How many questions on this test?
About 6.
6?
Yes.
On what?
There's 6 questions?
About.
Don't count on everything though. Where are you getting the number from? How many questions are there?
I'm telling you that's where we need to put those to be able to figure out how the pattern goes on this graph.
Oh, so when we get it, we just have to remember.
Yeah.
Oh, okay.
Yes.
It's only one.
Now then, the band of stability between this 0 and 15 mark, that's right on this bottom line. It's right on that bottom line. From there to there, it's right on that bottom line. Okay?
What you want us to do?
That's your band of stability. Put that mark right. You know, that's the band. That's the marking. That's the plot.
So we just make it dark?
Yeah, because that is where you have stable isotopes. Is right along that band. Okay.
Oh my God. Okay.
All right. After 15, then you need a smooth curve upward until you intersect here where these two lines come together.
That's when we do that little thing.
Yeah. Well, what I showed you the other day was if you use your wrist, okay, as a hinge, and just kind of play with it a little bit until you find the right angles and stuff, you can get a nice smooth curve like this. Okay.
Hey, look, my wrist ain't like that.
It doesn't have to be perfect, but you just need to. It just need to. I can tell it's a curve, and it, starts here and ends there.
My wrist is.
Well, I'm just saying that's a technique that might help you. Yeah, that's good.
Oh, I got it.
Okay. Now then, the only thing is, the last thing here is that. Yeah. Well, I can't really see the curve, but I guess so. All right. Along this band is where the stable isotopes are located. Okay. So we want to, but there's one more thing to do, and that is we need to widen out the band up here at the top. It needs to be narrow down here and wide up here. So all you got to do is just do this.
On that line?
On that line, and just it's wider at the top than it is at the bottom. Okay?
How far we gotta do?
Well, it's always comes down to almost a point down at the bottom, and just keeps going like that. Yes, you can. Okay? And so that's what the band of stability looks like. All right? So you just got to go to this 1-to-1 line, this 20-30 line here, stop at 82, and start turning upwards at 15.
Why are you giving us a test if you know nobody understands it? When you know it, like you know it, the fact that anything you know, everybody gets this stuff. You still get tested. Seems like you don't,
All right, so if you get out your periodic table, you can answer questions about the band of stability. Okay?
Are you gonna give us a test reference, right?
Yes, you use the yellow test references over here.
Can I pass them out?
Not yet. Okay? So let's say that I have is copper 58 stable. Is copper 58 stable? All right, listen up. 58 is the mass. The mass is protons plus neutrons. The atomic number for copper is 29. Okay? The atomic number for copper is 29. In order to find the number of neutrons from this, we take 58 and subtract 29, and you get 29. So this is the number of neutrons in this case. It's not always the number of neutrons, but it is in this case. Okay? So, is it stable? We're going to go to this band of stability. And we're going to go and look at where copper is for both the number of protons, which is 29, and the number of neutrons for 29, and see if it's on the band of stability or not. And that's really all there is to it. Okay, so copper has an atomic number of 29. It's right here. That number at the top is the atomic number and the number of protons. That's an isotope number. So I put this ruler right here at 29.
Where's 29?
Right here.
Can you make it obvious of where we can understand the work that you're trying to go over?
I put a mark where 29 protons is located. Okay? If I also put a mark where 29 neutrons is located, it's just off of the band of stability. So it's not stable. The stable ones are those that are on the band of stability. Okay, so if the atomic mass is 118, silver's atomic number is 47.
Oh, so 118 subtract 47.
Right?
Alright, I'm getting this a little bit, Mr. Taylor.
Alright, so this is the number of protons. The atomic number is the number of protons. Okay?
Hey, but the one above that, it was neutrons. So, oh, no, I got you.
Okay. And when you subtract then,
Now you get neutrons.
that'll give you the number of neutrons. Okay?
I got it.
Now we're going to take that number of protons and neutrons and go to the band of stability. Okay? Alright, so it says number of protons on the bottom, so we want to find 47 protons. Okay?
So all we're doing is just marking like, so the protons go across and neutrons go up and down. So all we're doing
Yeah, that's what we got down here.
so all we're
Proton.
doing is just marking the protons and neutrons basically.
Pretty much, yeah.
I
You're finding out where they meet here to see if they're on this band of stability.
so this is, I'm ready to take the test.
Alright, hold on.
Just like the only thing on the test, though.
Hold on.
Part of the test. Hey, is this the only thing on the test? Though?
No, we got one more thing to cover.
Oh, you need to keep coming.
So here's 42, 43, 44, 46, 48, so 47's right here. Alright, so that's 47 right there. And then we're going to find 71 neutrons, yes.
Okay, so you got, if it's not in the black line,
It's not stable.
but if it's,
If it's in the black line, it must be stable.
wait. Now that's a rest, so it's not stable.
Hold on 1 second. Let me mark this. And here's 71.
So even if it's in between the two lines, it's not stable.
That's correct.
Okay,
So it's not stable because it's not on the band of stability.
I got it.
So it
Got it
got to be
now?
on that band.
Yep.
Okay. Can I go to the
Alright. So nuclear equations are the last thing that's on the test. And for nuclear equations, all you got to do is figure out what goes in here.
Can I stay like, how you gonna fix this?
Yeah.
We just did something like this over there.
Yeah, we did this the other day.
I failed this
Ain't that
part.
was our homework?
Well, most people made 100 on the homework we did on this.
I know this.
Okay, then fill it in. Fill it in.
I'm gonna do it, watch.
Practice it while you got a chance.
Very weird. We can go to, for this part, we gonna have the, thing like, what's the, thing coming?
I hadn't planned on it, but I may give it to you.
Mr. Oh my gosh. Oh my goodness. And put that number in. Is it the B?
Yeah, that's the B one. Okay, so here we go. Neptunium on the periodic table has an atomic number of 93. Okay, the atomic number is the number of protons, and that goes at the bottom of these nuclear symbols, 93. Okay, we go over here, and this is 94. Well, element number 94 is plutonium.
Are you gonna give us?
So we're going to put Pu in here for plutonium, and now we got to figure out what goes in between.
Will you give us that? 0, -1. The middle part?
Hold on. Okay, so what number added to 238 gives you 238? Well, that has to be a 0. And what number here added to 94 gives you 93? That has to be a -1. And the only particle that has a -1 is beta.
Will you give us? Are you gonna give us like the symbols?
These are the 4 nuclear particles you got to know about. Everything else you figure out from the periodic table. Alpha, that's 4 and 2. Betas, 0, -1. Neutrons, a mass of 1, atomic number of 0. And gamma has no mass and no atomic number.
Alright, let's do this before I forget it.
Okay?
One more.
All right, I've been asked to do one more of these kind of equations, then we're going to do the test, okay?
Alright.
All right. What numbers go here for neutrons?
1 and
1,
0.
0.
1 and 0. Okay. What element and symbol goes here for 94? Pu. What goes right here for krypton?
36.
What goes here for cesium? You look up those in the periodic table.
We know.
Oh, I'm sorry. Okay. So what's going to go here?
Ian.
All we have to do is, a little n. Good. So, because a capital N means nitrogen.
Is that going to be 241?
This right here?
What's that for?
Let's find out. Okay. Let's see. We got Let's see, we got 85
That's going to 246.
plus 156. And this is 4 times 1, so that's 4.
Just kidding. That's wrong.
So plus 4, okay, is 245. But listen, I got to have a number that I add to 1 to get 245.
244.
244.